In this chapter, we're going to be studying stereochemistry, and basically what that is we're going to be looking at the three-dimensionality of molecules and the consequences that the 3D structure has on react and interact with other molecules. So to start this off, I want to look at a fairly well-known example of a molecule known as thalidomide. And you'll see that I have two structures drawn here. We have R thalidomide and S thalidomide. And if you look carefully at these two structures, you'll notice that the only difference in them is on these carbons. And essentially it's just in the three-dimensionality. On the top structure, we have this large group coming out of the plane toward you. On the second structure, you have this large group going back into the plane away from you. This compound was extremely popular in the 1950s in Germany and several other countries. And what they did was they prepared thalidomide as what's known as a racemic mixture, and that just means they prepared it as an equal mixture of these two. And what we're going to find is that when we do chemical reactions that produce these new three-dimensional centers, it's much easier to produce as a one-to-one mixture as opposed to producing either of these pure. So that's why when they were preparing this, it was much easier just to make this racemic mixture of the two and use that. And in fact, they did testing on rats and found that no matter what concentration this molecule was given to the rats, it would not kill them. So this was marketed as a safe drug, specifically as a non-barbiturate sedative, and it was almost as widely adopted as aspirin at the time. In many countries, with the exception of the United States, the FDA head at the time just didn't think there was quite enough data on it to fully approve it as an over-the-counter medication. But it was undergoing clinical trials in the US at the time. But during the 50s, this was widely used as a sedative, and there was an OB doctor that found that it also had an off-label use to prevent morning sickness. And he started prescribing it to his patients for morning sickness, and that trend continued, and it became quite popular for that purpose. Unfortunately, as he began to deliver patients from mothers who were taking this drug, he found that many of the babies actually had birth defects. Specifically, they had shortened and deformed limbs, or sometimes even missing limbs. By 1962, this drug was pulled from the market and banned entirely. More recently, it has come back onto the market as a chemotherapy drug, but it is very carefully prescribed that anyone that's taking this cannot be an expectant mother. Subsequent studies, however, found something kind of interesting, and this is a case for many other molecules as well. But the two different molecules here, and these are known as stereoisomers. So they're three-dimensional isomers, and we're going to get into that here in just a bit. But between these two stereoisomers, the R version is completely harmless, while the S version is a tetratogen. Which means it causes birth defects. So what this example does is it paints a picture to show us how important the three-dimensional structure of molecules is. And we're going to see that through some other examples later on. But this particular case here actually led to the strict drug approval process that the FDA currently undergoes for any drugs. But also, anytime a pharmaceutical company now makes a molecule that can have different stereoisomers, every stereoisomer has to be prepared independently and tested independently. The whole reason behind this is the fact that our bodies are three-dimensional in their nature, and we have different receptors with active sites, and one molecule might fit into one active site, while another molecule, because of its 3D structure, will fit into an entirely different active site. So the three-dimensional structure of molecules has a huge consequence on how these drugs work. This is why, as chemists, we must have a fundamental understanding of the structure and properties of different stereoisomers. Let's start off with a few definitions. The first is just what isomers are, and we've talked about this before. Isomers are different molecules, but they have the same molecular formula. But there are some subclasses of isomers. The first are constitutional isomers, and this just means the atoms are connected differently. So let's look at an example of constitutional isomers. Okay, so here's a six-membered ring with a two-carbon chain coming off of it. If you count up the carbons and hydrogens, it's C8H16. But we can draw a different molecule. We still have a six-membered ring, but now I have the two carbons here and here. But this one is also C8H16. But of course, the connectivity is different. I've essentially taken this carbon group, broken it from here, and attached it to here. So these two represent constitutional isomers. Now our second definition is stereoisomers. Stereoisomers have the same connectivity of atoms, but different spatial or 3D arrangements. One case where you have stereoisomers is with double bonds. Remember, double bonds lock these groups into place, so there's no free rotation. In both cases, you have a four-carbon chain, so the connectivity is the same, but three-dimensionally, these are different. In this first one, you have these two methyl groups on opposite sides. On the second one, you have the two methyl groups on the same side. So these have different 3D arrangements. These are stereoisomers. All right, and let's actually look at this dimethyl cyclohexane here and give it some three-dimensionality. One option is to have both of these methyl groups pointed out towards us. Another option, let's have one out and one back. The connectivity is the same. It's still, or they're both 1,2-dimethyl cyclohexane. but they are in fact different molecules because of their 3D structure. Essentially, this carbon here, the group, has been inverted. Since the 3D is different, these are stereoisomers. To understand 3D structure, we first have to understand the concept of chirality and asymmetric centers. Asymmetric centers are also referred to as chiral centers and sometimes even stereocenters, but later on we'll look at the difference between the two. But I'm going to stick with the term either asymmetric center or chiral center. And what that is it's a specific atom, typically carbon, that we're going to be looking at, but an atom that's bonded to 4 different groups. And the key here is different. sp3 carbons are always bonded to 4 groups, but the question is, are they different? So let's look at some examples and figure out whether or not we're looking at chiral centers. In fact, we don't even need to worry about 3-dimensionality yet. The first one, this should be pretty straightforward. So if we look at this and look at the groups around the carbon, you have a hydrogen, an OH, a Cl, and a Br. Those are, of course, 4 different things. So that particular carbon is bonded to 4 different groups. That's a chiral center. And we often denote that with an asterisk on the atom. Okay, how about this one? Specifically, I'm interested in this carbon. All right, when thinking about this, my first recommendation is that you draw in any implied hydrogen on the carbon you're examining. So this carbon has 1 implied hydrogen that I'm going to go ahead and draw in. From there, if we look at this, your first instinct might be to say, well, this carbon's bonded to a carbon, and a carbon. 3 carbons, those aren't different. But you need to take the group as a whole. Anything that makes that group visually different is enough to consider it a different group. This one is 1 group because it's a CH3. This one is different because it's a CH3, or it's a CH2CH3. It's an ethyl group. And then this 3rd carbon is different because it's a 3-carbon chain, a propyl group. So anything that can make that distinct is enough. And then our 4th group is the hydrogen. For that reason, this carbon is bonded to 4 different groups. And we're going to mark that with an asterisk to show that it is a chiral center. All right, one other term that we can kind of take in here a molecule with 1 chiral center is a chiral molecule. Now there's going to be other things that fall into this class of chiral molecules, but one thing you can always take is if you have 1 chiral center, the molecule will be chiral. Let's look at one other example. Right, if we look at this one here, and we want to look at this central carbon, Alright, what you should immediately recognize is that these two are both ethyl groups. They're the same. For that reason, this is not a chiral center. Okay, and that's also why you never have to worry about CH2 groups being chiral centers, because there's always 2 hydrogen there, so there won't be 4 different groups. Now I have one here for you to take a couple of minutes to try. So go through this molecule carefully and look and see if you can identify all of the chiral centers and then decide how many there are. What we're going to do next is take this first chiral molecule that we looked at and actually draw it and visualize it in 3 dimensions, because right now everything's drawn as flat, so you don't know really what the 3D structure is. When you're drawing a chiral center in 3D, you always want 2 bonds in the plane, and you draw those as just straight lines, so here could be 2 bonds in the plane. You want 1 bond out, which will be a wedge. And you want 1 bond back. Which we draw as a dash. And when drawing this, a really, really important note to take here. Always draw your dash and wedge coming off the large angle of the bond. So what does that mean? I'll show you 2 versions here. Okay, here's your large angle. Here's the small angle. Never draw these groups in the small angle of the bond. If you draw it like that and like that, that's wrong. What's correct is to take them and draw them from the large angle of the bond. It doesn't really matter which side you put which on, though. So be careful about that, because these structures down here imply the tetrahedral nature. This implies some weird pyramid-like structure. Alright, so now let's take this base molecule up here, and I'm going to keep the H and the OH in the plane. You could pick actually any of the 2 groups, it doesn't matter, but I've decided I'm going to keep those 2 bonds in the plane. So we'll draw that. And then I need a dash and a wedge group. So maybe I'll put the bromine on the wedge and the chlorine on the dash. Notice, even though I've drawn this kind of rotated around a bit, the dash and the wedge groups are still coming off the large angle of this bond. Okay, but it would also be perfectly valid to draw the chlorine coming out and the bromine going back. here's my chiral center. And really the difference in these two is just that the two groups are inverted at the chiral center. These two molecules are a pair of stereoisomers. And next we're even going to learn more specifically what these two stereoisomers are called. They're actually called enantiomers. We can use a simple calculation to figure out the maximum number of stereoisomers that you could potentially have. The calculation for the maximum number of stereoisomers is you take 2 to the power of n, where n is the number of chiral centers, and later on we'll even learn that n can equal the number of stereocenters. So for this particular molecule, there's one chiral center, so we do 2 to the first equals 2 stereoisomers. So as you gain in the number of chiral centers, the number of stereoisomers increases exponentially. As you progress learning stereochemistry, I want you to get comfortable working with molecular models. So here I have the two stereoisomers from the previous slide drawn in, and then I have molecular models of each of these built. And what I want you to see is, we have a white sphere, that's the hydrogen. So we have the hydrogen in each one. And then we have the OH group, that's the red sphere. So there's our OH group. These bonds represent the plane. And then the blue sphere is representing the bromine. And on this first model, the bromine's coming out towards us, and the chlorine, which is green, is pointed away from you. So think of this as the plane of the page, and then going behind is the chlorine, coming out is the bromine. So there's the chlorine. On the other stereoisomer, we have the H and the OH in the same relative orientations, but the green chlorine is now coming out, the blue bromine is going back. So what's the difference in these two molecules? Well, one, we know that the two groups, the OH, or the bromine and the chlorine, those are inverted. Okay, but in terms of defining the relationship between these two, the first thing we're going to say is that they're non-superimposable. Okay, now what that basically means is if we take one of these molecules and try to superimpose it on the other, well, the H and the OH, those line up and those superimpose, but the chlorine and the bromines, those don't line up, they won't superimpose. No matter what you try, you can never get these molecules to perfectly superimpose on one another. Another way to almost think about non-superimposable is just non-identical. Okay, but also if we start to work with these molecules a little bit and we look at maybe a relationship between them, if I spin this one around, these two molecules are perfect mirror images of one another. So if you had a mirror right here between them, they're reflecting one another. There's a mirror plane right here. So these are mirror images of one another. And you can show those mirror images from a variety of viewpoints. It doesn't have to be these particular atoms. You know, I could flip these around and show the mirror image here. Or here. So there's a lot of ways to see that they are mirror images of one another. So stereoisomers that fall into this definition, non-superimposable mirror images, we call these enantiomers. Let's take a look at another pair of stereoisomers here. We have these two molecules, and I've already highlighted the chiral center for you. And you'll notice the only difference between the two is that I've swapped the position of the two groups. A new abbreviation you may not be familiar with is this pH. And what that is, it's an abbreviation for a phenyl group. And all a phenyl group is just a simple aromatic or benzene ring attached to the molecule. So if you see pH, that just means this ring is attached there. Now these two molecules look very, very similar. The only difference is in the 3D configuration of the chiral center. And this is going to be a little bit reminiscent about what we talked about with thalidomide, in that the first one, it's called levomethamphetamine. And it's the active component in a Vicks vapor inhaler. In fact, you could run down to CVS and pick up one of these inhalers and it would be full of this levomethamphetamine compound. In comparison though, the other stereoisomer is methamphetamine. The psychostimulant. So just the subtle change of inverting the configuration at the chiral center, we go from a pretty much harmless legal drug to a very dangerous illegal drug. And again, this kind of hammers home the point that biomolecules in our bodies are chiral. The active sites, they're designed specifically with certain shapes so that certain molecules fit in there appropriately, and the different stereoisomers will interact differently with the biomolecules. So basically, biomolecules are chiral, thus different stereoisomers interact differently in the body. All right, now we've already essentially talked about this, but let's think about the relationship again between these two. All right, now I'm going to take this first one and redraw it. I'm not going to draw the hydrogen in. I'm just going to draw the dashed methyl group. Okay, and then what I'm going to do, if you'll notice, I have the phenyl group on the left, and if I want to make a mirror image, I need, for the other molecule, the phenyl on the right. So what I'm going to do is take this molecule up here, and flip it horizontally. So if I flip that molecule horizontally, this nitrogen with the methyl group will be on the left, the phenyl will be on the right. Okay, but that brings up another important point when you flip something over. Right now, this methyl group is out. If I flip this molecule over horizontally, it ends up going to the back. Let me again prove that to you using a model. Here's a molecular model that I built for this compound. I'm using the green sphere just to represent the phenyl group right here. And then we have the CH2 group, which is right here. Next, we have our chiral center, and that has the methyl coming out, the hydrogen going back, and then finally the N-methyl group. Okay, so what I want you to do is watch as I rotate this or flip this horizontally. All right, I want you to keep your eye on this methyl and the hydrogen at the chiral center. Right now, this methyl is pointed out toward you. If I rotate this or flip this horizontally, now the phenyl's on the right side, just like it is down here, but notice how now the hydrogen's out and the methyl is back. So anytime you flip a molecule horizontally, your dashes and wedges go from out to back or back to out. Again, so right now, this methyl group is back. If I flip this horizontally, now this methyl group's pointed out toward you. So that's all we're doing. We're just flipping this molecule horizontally. We didn't change the molecule, you're just moving it in space. Just as in our previous example, these two stereoisomers represent a pair of non-superimposable mirror images. So they're therefore called enantiomers.